So let's suppose we're given a retrosynthetic analysis question like this, where we are given some sort of molecule where we have what looks like an ester up circled in yellow, and then down at this bottom part we have what looks like some ketone with some alkyl substituents to it. We can simplify this down. We can name it a little bit easier. We notice our main group that we're going to worry about is our ester, because that's how priority goes. Um, from that ester, this is going to be our alpha position, and then this is going to be our beta position. And so we can say that this is a beta keto ester, which makes it a little bit nice to understand what we're working with here. And so our question says, this is what we make. We make this beta keto ester, but we need to figure out what we used to get to this beta keto ester. That's what the question's asking. So um, if you want to try it on your own, go ahead. I'm going to go into an easy way to do this, um, and that would be through the Claisen condensation reaction. So what is the Claisen condensation reaction? Well, let's work through it. Um, it's going to be, and actually let me write down some things we're going to be looking for. Claisen condensation. And my pen had an issue. There we go. So things that you'd look for, I would say look for repeating carbonyl substituent, alkyl groups, and I'll go over what I mean by that in a minute. And then also look for is there an ester? So looking up here, and I will redraw it, do it in this color. And that first question I posed, we had this thing. And so if I'm looking at just these little bullet points I wrote down for us, are there any repeating carbonyl substituents or alkyl substituents? Well, I'm looking at my carbonyl being well, this one and this one. And on this ester one, I'm looking to the left and I see there's a methyl substituent, so that's great. And now looking down at the bottom one, so let me recolor that in blue. Looking down at the blue carbonyl, I'm looking at the substituents both up and down, and I see a methyl group to the right, so kind of down to the right. And I'm also seeing what could be like a single carbon going straight up, because I don't care about the thing that comes after, just simple carbons. So that's telling me that I'm dealing with only single chains or just single methyls. And so that gives you kind of insight that you might be working with some sort of a Claisen condensation here. And then I also see that there is in fact an ester. And so if you're thinking Claisen condensation, it's probably a good idea to go ahead and try and see if you can figure this retrosynthetic problem out doing or going through that mechanism. So let's go through this. Just going to clear the board real quick. Okay, so what are we going to start with? Well, the Claisen condensation includes using esters. That's the main purpose, or the main giveaway to the Claisen condensation. So I am going to start with this specific ester, and I'm going to do something with it. I'm going to add, I'm going to add some base so I can deprotonate the alpha position. So that base I'm going to use is going to just be hydroxide, just generic. I'm going to draw this H out, and now let's just push electrons. I'm going to take something from the highest energy and do something with it. So in that case, that's our hydroxide. So hydroxide wants to pick up that proton. When it does that, the electrons that were holding it to the alpha carbon are going to be flopped down, making an enolate essentially. So that enolate looks like this. Right. Now from there, we should recognize that, well, of course, resonance can happen, and we can get a bunch of different things happening here. But first, before we do that, let's recognize that what we have in solution right now is a whole bunch of this starting ester. So I'm going to write it again over the arrow, just because I know there's more of it. I know there's more of it floating around. So from this point, let's do that resonance. So I'm going to take something with the highest energy, just move it down, and I'm going to draw the electrons going from this double bond that's going to move because of resonance through this carbon, through that carbon, and I'm going to have it attack that carbonyl. Because we know that that part of the carbonyl is very delta positive, because it's delta positive, it wants, it's electron deficient, and so it's going to want to attract electrons to it. So when you do that, you have to bump electrons up onto that oxygen. And we get our next intermediate. And of course, this is getting closer to what we want, but it's not quite there. And so we need to do something else. Now, we know, skipping ahead, if you want to try to figure this out, go ahead. But skipping ahead, we know that um, we can make O minus be a good leaving group under the right conditions. In this particular case, we can make O minus leave, and in particular methoxide. And so how are we going to make methoxide leave? Again, take something with the highest in energy and do something with it. So we're going to take our O minus, let the electrons come down to remake that carbonyl. When it does that, it'll break this bond between the carbon and the oxygen. Oxygen takes the electrons and leaves as methoxide. So down below, what do we have? We now have essentially our product. There's just one small caveat, and it's really not even an issue. So at this point, come on, there we go. And we now have a lot of methoxide. I'm going to just write this. We have this methoxide floating around in solution. And so what's it going to do? It's going to notice that there is a proton over here that wants to fall off. And so it's going to go over to that proton and pull it off. And so if you're given a problem like this on a test, you should recognize that yes, you do have what seems like the final answer. You got to it, but you need to add one more thing after this, and that's just simply going to be the addition of some weak base, or I'm sorry, some weak acid. So we get to this point, and now we have a minus there. And now what we have is just methanol floating in solution, and there's not going to be really anything else that methanol is going to do to ruin our reaction here. So as a last step, we're just going to introduce some acid. So I'm going to use just use HCl. And as we show our electrons, and I did say weak acid. You want an acid that's not going to have a strong conjugate base. Because, of course, if you do, then um, this proton that would get replaced right there would eventually be able to be pulled back off, and that's counterproductive to what we want in the end. So, as our final answer, we get to what we wanted, and we did it via the Claisen condensation way.